Hello everyone. Outcomes for the lesson. Here we are going to define or give the concept of reverse of differentiation. We'll use table of integrals while doing some examples on them. And the last outcome for the lesson is different integrals. So three major things we are going to do here. One is reversal of differentiation, another the use of table of integral, and the last one, what are different integrals. Okay, differentiation in reverse, what does it mean? If we have a function y equals x square and we take its derivative, which comes to, so it means the derivative of x square is 2x, and the reverse of the derivative 2x is again x square. So this means reverse. How to reach to this x2 again? How to get this value again? Well, and we call it, this 2x is integration of x square as well. If we see, so they are reversible, and x square derivative is 2x, and it means 2x integration is x square, so reversible. Let's do some examples. Derivative of x square plus 4, derivative of x square minus 15, derivative of x square plus 0.5. All the three functions giving same results after taking differentiation. So it means the derivative of 2x can be this answer, can be this answer, and can be this answer. So which gives a concept that while we are going in the reverse, an extra number should be produced. While in the differentiation, if you see, this extra number is disappear here, this extra number is disappear here, and this constant is disappear here. But when we are going back from the integration, these extra number are produced. So we can say the integration or the reverse of the differentiation of 2x equals x square plus c. In this case, the c is 4, and in this part 2, the c is minus 15, and in this case the c is 0.5 or plus 0.5. So integration produces one constant number. So c equals 14 and 1, c equals minus 15 and 2, and c equals 0.5 and 3. Formally, integration or the reverse of differentiation is represented by this symbol, snake-like symbols, and it has got this notation as well. So whenever we are taking a reverse or antiderivative or integration of a function, so this symbols and this differentiation symbol is important to be expressed with it, because this shows here may be another variable with it, suppose y. So we are not making changes in y, we will make changes only in x. So this differential is very important. So the nomenclature or the terminology involved here, this snake-like symbol is known as sine, integral sign. The function we are going to integrate, what we are taking reverse or we are taking antiderivative, is known as integrand. Differential symbol is necessary to be added all the time, and one more thing, that c should be produced in the answer, which is called constant of integration. So constant of integration should be added all the time when we find integration. This sign once will be removed in the definite integral. When we reach there, we'll learn that there. Here, okay, rule for constant, so it is just the first rule. So this rule will be used here. Example, so I already did some example, x7. Which rule is supposed to be used here, and I think it's very much clear. Rule 3.1 will be used, x7. So let's see my slide work. Yeah, and look, rule 3 is used. Then this is our final answer, and this thing is important, don't forget it. It is always found in antiderivative or simple integration. Another check, differentiating the answer. So if we differentiate it, so according to rule of the derivative, this will be reduced by 1, so 7. Here is 8, and derivative rules tell us that if you have a constant, it will be straight away 0. That was, I think, the first rule. So now let's see my slide work. I hope everything clear. So see, again we get the same result, and that is why it is called antiderivative, reverse of differentiation, or integration. Integration is general name, it will be used throughout the lessons. Okay, so now let's go to another example. Yeah, this is also from trigonometric functions. I already did this. Let me go it quickly. Which rule? Rule 6.2. This is 6. and 2. So if there is any k comes under it, and the k is 5, so 5 will be here, and don't forget this 5 will not disappear here, and this is the thing we will be using. Example 1.5. This time I'm using rule 5.2. If there is a constant, so divide by constant again. In both the cases, divide, rather here also. In this trigonometric function, it will be divided. So first of all, minus is in the product minus will be appear, then cos of x by 2 and nav divided by k. I should have written that this is actually sine 1 by 2 x. So this is k. These two expressions same, so divide by k. And divide by this, it will become 2. Don't forget minus. So minus 2 and cosine of x by 2. Yeah, this is the angle. Well, now let me see my slide work. So almost the same thing. Okay, let me make my screen clear so that you could see the neat slide work. So see, almost same. You use bracket or not, it's up to you. This is k, and the k, rule 5.2, and final answer. So it means this is divided by 1 by 2. So when you remove division, this will be reversed to 2 by 1 or only 2. So this is the answer. I was here. So this is a constant. First rule is I displayed. Now this doesn't have any variable, but there is one. If there is nothing, all the time we take it 1. So here it is 1, and according to our second rule, I think it will be x, and this. So first rule, yes, first rule, with there is constant. Next slide, we are doing an example from the book, and this time we have two functions, x cube and sine of x. So two rules will be used. So first of all, what is the rule by which we can split this into two integrals? So that is rule 20. Okay, rule 20, but we have addition. So for this I will write this is only plus. It will be equal to the plus of f and g integral. So two integrals. First integral, x cube 3, answer is this. It was x3, so according to the third rule it will be 3 plus 1, and then it will be divided by the same 3 plus 1. This is what rule number 3 2 tells us, and plus constant of integration again. And this one is 5a, we did it 2 times I think, so no problem. So c1 and c2 will be produced. So in the next step, c1 and c2 can be added and we get neat answer, which is we can call it c. So instead of writing two c's, we write one c. And I explained this, we use this rule. This is 3-1. We use rule 5. Rule 5i is this one applied here, and 3i rule was used here. Okay, let's see my network. Opening or removing the brackets, and the same thing as I told you, that both the c will be added to a new c. So if you have 3 terms, if you have 4 terms, how many terms you have, even you don't need to write your c's. If you don't write your c here and here, but it is important, this is important, at the end you will write. If you don't do these things, no problem at the end. So you can remove this from here, c2 from here, and of course you don't need this, but at the end this is important. c1 and c2 I gave you for concepts. Maybe at the later stages some student ask, why 1c you are putting there, 3 times 4 times? So actually this is the sum of c's. So to make clear that point, example, bigger example from the book about the structural engineering. I think there is some image involved as well. Okay, so let me highlight important things, then we will discuss. First of all, the length. So the length I have mentioned here, which is, this is length. the length of the rod or the beam. Okay, it carries load W. So here on the top of it there will be some load. Okay, it is just mentioned. The load can be anything. They can be boxes, they can be heavy machinery, that can be anything which is being loaded on it. Okay, introduced bending moment. Bending moment, when we put load on something which is in the air, so it is natural when the load exceeds, there will be some bending. I'm sorry with this drawing. Let me try to make it more clearer. Okay. So it will be bent under the weight. Okay, and the shape will become like this. So it is bending. Now the beam is bended. So M is bending moment. The load is increasing, it will be bending moment. Engineering term, scientific. Okay. M or the bending varies with X. What does it mean? It means if oh my god, the bending and let me change the color. The bending in this area is less, then it is increased, and the more we are going, the bending is increasing. See, so the bending is increasing when the length is getting increased. So see, bending is increasing at the middle, at the center, and at the end again the bending is decreasing. So bending, so the bending is giving us a curve like this. First it was straight, now it is curved. Okay. Color, change color. Okay. Now it can be shown that the bending moment M is related to force V. Of course, the weight is putting some force on the beam, and which is expressed in this shape. Okay, the change in the moment force is given another name, shear force. We call it shear force. So as we go to the middle, the shear force, the rate in the shear force is increasing, and then when we move to the ends, to this end or this end, the change in the moment force is decreasing, and change in the moment, it is the rate of change of the moment force, and we call it shear force. And shear force is this thing. The structural engineer has modeled the shear force, this thing. Okay, now the rate in change in the shear force V is actually the rate in the change in the shear force, so which is this. We will integrate it force, the bending force, and we will calculate the bending force now. So actually we are going to calculate this integral. We are going to do integral. Okay. So now it's a game of rules, laws, integral laws, plug in values. And if you see here, this I wrote this constant outside first time, w by 2 integral L minus 2x close bracket and dx. Okay, and after that w by 2, okay, and we split this into two integral dx, and of course the w by 2 will be multiplied here, w by 2 integral to x and dx. But again, the game is not over. Still we have some integral constants. So see, this L is constant and this 2 is constant. So they will go outside and we will get this expression. So I think this explanation is enough. Now here we have 1, so its antiderivative will be okay x, and here again here it is, we have x, so it will be x 2 by and 2, and of course don't forget they will come here plus they will come here, and when you finish the answer there will come 1c. But if you are very systematic and you want to write some note for you and you want to write both c's together, so I have mentioned them. You can oh, this yellow is not visible, so if you like do not write this, your option. At the end only 1c is enough. Okay, again if you multiply this L inside or all the things inside, again they are constant. 2 is constant, C2 is constant, so okay, so look at them, they are constant. So again answer will come another C and W by 2. So if you are not doing this step, so no problem. If you are not doing this, so it means if you don't put the C1 here and C2 here, so you can finish this quickly and just at the end put 1C. Okay, but this is for the sake of explanation. Another definite integral now. Okay, definite. Before this it was not definite, now definite. Definite means when we put limits. This is upper limit, and this is lower limit of integral. And of course they are the value of x. Look, the variable is x, the function is of x, then this is x value. Look, not, they are x value, so we are putting limit on the main variable. Okay, this is for neat work. This integral is commonly written as ab, if so note, no need to write x. Now onward it should be clear that a is actually x, b is actually x. This is x is line 2 points. For example, if we have a curve like this is f of x and this is a and b, so we are doing integration of this curve from a to b. Okay, this concept will come in the next lesson. Anyways, a and b is this thing. When you evaluate a definite integral, the final answer will be a number, this time number, while in the previous antiderivative they were just coming expression with the production of c. Let's take an example, x2, okay, and if you see rule 2(1) comes this, and since we have limit, so upper limit will be plugged in here first, look, and the same thing will be repeated. Then we will write minus. Now the same bracket will be done for 1. If there is any x, plug in x value. No more x, that's it. Now removing brackets, simplifying numbers, and this c and this c will be cancelled. So this number in the definite integral, we don't see any constant of integration. Constant of integration is given in antiderivative or the reverse of differentiation. In definite integral there is no c. Okay, but for the sake of concept I explained here that if c is coming, that c will be automatically finished, so you don't need to write c. Answer is 21 without c. Okay, let's go to another example. Two terms. In both the examples, and this time I am playing with the power. So look, limit lower is 2, lower is 1, and upper is 2. Here the lower is 2 and the upper is 1. We are changing them. Okay, changing the limits. So let's see the first one, solid. Okay, still I'm using constant of integration, but if you are clearer now, you don't need this thing. You don't need this thing. This I am doing for very documented thing, that it is like this. But if you don't write in your work, nobody will mind it, and everybody will accept it, and everywhere it will be accepted. Okay, so removing brackets, c's will be finished again. So why are you writing c? No need. Let's see the other one, 1, 2, applying rules from the antiderivative or the integration table. The table is same. The table is same, but the only problem there, in the table constant of integration is produced. Here you don't need to constant of integration. Okay, and when we do it, the clear difference in the answer is minus. So when we change the limit, the only difference will be, the answer will be minus. So this is a rule of integration or definite integral. If we change the limits, negative sign will be produced in one of the answer. So this is one of the key point you can be asked in any of the quizzes. Again, civil engineering, the force on the wall of a tank. This is tank. Okay, so the height, the total height of the tank from here to here is d, and this is a cuboid. Cuboid mean that this all side, this side, this side, this side, they are all same. L equal to W, they are all equal, and W equal to L. Anyways, for certain calculation we are using L and W, otherwise concept wise they are same. Okay. Still the statement of the example. Here is a pressure of water on depth h. If something here in the some part is inside the water, this all is water. Okay. So at this height, is this pressure. Okay. So this is the height, this is total height, d is total height of the tank, and the thing floating inside the water, swimming inside the water, height of that is here. Well, Mr. Pascal in 17th century calculated this pressure is rho gh. This is rho, symbol like this, not p. Okay, I try to write again. So same. Rho is density of water and g is gravity constant. We use it a lot in physics when we are doing with velocities, vertical movements. Okay, it can be now the force exerted on the wall. So all around there is forces of the water which is putting pressure on the wall. Okay, all walls. So the force exerted on the wall of the tank given by the definite integral. This civil engineers modeled the force exerted on the wall this. So rho is density, g is constant integration, and w is actually the width, and d is the total height of the tank, and z is the variable. Okay, z is the variable. Z actually is this axis. Okay, so on a y-axis and x-axis, look, if the water is here and here, then this will be the height of. So see, now if we add more water, so the height is increasing. So our variable is actually z. The x and the y, this is y-axis, x-axis, and this is a y-axis. So x and y are not changing because there are walls. But when we are adding water, the height, the water is gaining height or the water is losing height. So height is related to z. Okay, so this is important. Let me change color. Okay, now let's solve it. Evaluate the integral. Two questions are there. Part B is not that important. The books has solved it and I have also solved it. The important thing is evaluation of integral. Okay, from 0 to D. From 0 to D, when the depth at the bottom and capital D is actually the total height of the tank. What are the things common? Rho, G and W. Width of the tank is constant. D is also constant. So this time I'm not separating them into two variables. I'm doing them in one. When you get expertise, so you don't need to divide them into two integral. You can do this in one integral. Like the D is a constant, so dx, and this is x, so x derivative is x square by 2, and of course minus is coming minus. Still I'm using c, no worries, but I'm telling you, you can remove it. Okay, now it's the turn of limit. Now let's play with the limit. So two brackets will be produced, one for D, one for zeros. If you have, they are actually Z value because our main variable is Z, and this is also Z. So one time we will plug in Z is D. So see, I plugged in here D, so it becomes D square, and when you plug D here, so D square. No more I'm writing C because they will be cancelled. When you are writing Z square, sorry, Z0, so this will become 0 and this will also become 0. Okay, so this is a number. Rho is a number, G is a number, width of the tank is a number, total height of the tank is a number. Okay, P, I'm not going into that detail. Rho at pressure at height H is rho gh. Mr. Pascal gave this expression. Pressure at 0 when there is no water, so there will be no pressure, of course. Pressure at the base of the tank is rho gd because this is top of the tank. Average pressure, so if we take average of the pressure at the depth h and pressure of the tank, we take this half rho g. So take typical average. Area of the wall is because the tank was like this. Okay, this was tank. It is height is if this is height and this is width, so this will be area of the wall, area of the wall. And now using this result, because they are asking about this, which is here, if we split this into two factors, this dw, so dw square can be separated into dw and one of the d will be left here.